All right, welcome to thermochemistry. Today we're going to talk about enthalpy, heat energy, and what we call bond energies. To answer the essential question, how can we calculate the heat energy of a reaction? All right, so in order to have these discussions, some vocabulary terms are necessary to talk about. We're going to start talking about what we call systems and surroundings. So a system is just a thing we're talking about. In chemistry, we'll usually be talking about a chemical reaction as our system, and the surroundings is just everything around our system. Or if you've ever had a campfire before, your system might be the campfire, and the surroundings is you and your friends roasting marshmallows. Right? So that system is just a specific part of the universe that you're talking about, and the surroundings is everything around that system. We need these two terms in order to talk about something called enthalpy, which is the total heat energy in a system. All right, so whatever system we specify, we can tell what the heat energy is, but only if we say what the system is. We represent it with the letter H for heat, and it's measured in kilojoules. Any change in enthalpy is written as delta H, this delta meaning change in. When we are talking about enthalpy, we can have two scenarios arise. We can have an exothermic process or an endothermic process. In an exothermic process, this is any process where heat energy exits a system. So if you were to light a campfire, the heat energy stored in the log when you start burning it is released, and you can feel that heat. The enthalpy change in this case is negative because the system, your campfire, the amount of heat that it has is decreasing. After your fire is burnt out, there can be no more heat removed from it. It's already burnt. So exo is this prefix here meaning exit or leave. Heat energy is leaving the system. Endothermic is the opposite. It's any process where heat energy enters a system. Enter, endo. Enthalpy change in this case is positive because the amount of heat in the system is increasing. Endo is enter. Okay. So you can think about like hand warmers. If you hold a hand warmer, the heat energy is leaving the hand warmer and going to you. So the heat enters your hands, and so that's endothermic for your hands, but exothermic for the hand warmer. Now, in order for any of this to work, we have to talk about the law of conservation of energy. This states that energy cannot be created or destroyed. It can only change forms and locations. So if you use a hand warmer, however much your hands warm up by is how much heat energy that the hand warmer has lost. Because it can't be destroyed, it can only just change locations from the hand warmer to you. All right. So these vocabulary terms can be a little bit tricky, so some practice is necessary. All right. Talking a little bit more about exo and endothermic so we can get some solid examples. Again, exothermic heat energy exits a system. So this animation shows the system, and these arrows that say heat on them are leaving the system and going to the surroundings. The surroundings are changing color to show that they're warming up, and the system is cooling down. In this case, endothermic heat is entering the system from the surroundings. So the system gets warmer, but the surroundings gets colder. So whether something's exo or endothermic depends on perspective. So going back to that hand warmer example, the hand warmer is cooling down as you use it. So for the hand warmer, it's in an exothermic process. Its heat energy is being released. For you, though, in your hands, it's an endothermic process because heat energy is entering your hands. So that's why we need to specify what our actual system is, the thing we're talking about. If we're talking about the hand warmer, the process is exothermic. If we're talking about your hands, the process is endothermic. As some other examples to help you out with that, exothermic reactions, an explosion or fire releases heat energy to the surroundings. You can physically see how hot this is, and all this heat is leaving whatever explosive you detonated. On the opposite side, ice absorbs heat from surroundings when it melts, which is why it feels cold. When you touch ice with your hand, the heat from your hand goes into the ice cube to melt it. So you are feeling cold, but the ice cube is getting warmer. Now, that can be a little bit challenging again if you're not specifying your system and surroundings. If we're talking about our ice cube as our system, heat energy is entering the ice cube, but it's also leaving your hand. So for your hand, it's exothermic to hold an ice cube, but for the ice cube, it's endothermic because heat is entering the ice cube but exiting your hand. So there's one other thing we're going to have to talk about here with enthalpy and energy and heat. We're going to talk about bond enthalpies. So for that explosion on the previous slide, or any chemical reaction, energy can be held in bonds. All right. So a bond enthalpy is just the energy of a bond. This is the energy required to break a bond or the energy released when we form a bond. This bond enthalpy is measured in kilojoules per mole. So we can imagine bond enthalpy sort of like an energy price to buy or break a bond or sell, form a bond. Now, here's where some people get confused. It takes energy to break a bond. So in order to break a bond, you have to put energy in. But energy is released when a bond is formed. All right. So if you take a look here, here are some bond energies, bond enthalpies for some different types of bonds. And hydrogen-hydrogen single bond is 432 kilojoules per mole. But something like a nitrogen-nitrogen triple bond is 941 kilojoules per mole. So what we generally find is that triple bonds have the highest bond energy or price if we're talking about buying as breaking and selling as forming bonds. Double bonds have the next highest, single bonds have the lowest. And then intermolecular forces have even lower because they're not actually bonds, they're just really weak attractions. So to kind of help us solidify the idea of breaking bonds, it takes or costs energy to break bonds. This table shows us the cost of these different bonds, how much it takes to break them. In the case of a nitrogen triple bond, it takes 941 kilojoules per mole to break. So we can imagine the energy as being absorbed by this bond, which causes the nitrogen atoms to separate, and now these nitrogen atoms are in this high energy state. They absorbed that energy, that bond has gone away. The oxygen-oxygen double bond, not as high of energy cost, 494 kilojoules per mole, but we can again imagine the bonds absorbing that energy. The atoms pull further apart until that bond sort of just vanishes, right? So they're being pulled apart very slowly. In this hydrogen single bond, we can imagine is 432 kilojoules per mole to break. So we can imagine it absorbing that energy, those atoms separate, and now we have a bunch of atoms that have been separated. And it cost us this much energy to separate those different bonds. Okay. So on the flip side, if 941 kilojoules per mole could break a nitrogen triple bond, when a nitrogen triple bond forms, that much energy is released. So if we watch here, as these bonds form, energy is released. And so that energy that we use to break those bonds is also the energy released when we form those bonds. So this nitrogen triple bond, which was super expensive to break, also gives us back a ton of energy when it forms. Similarly, the oxygen double bond, the same energy it took to break is the same energy it took to form. For these hydrogen single bonds, the same energy it took to break is the same it took to form. So these energies are the cost or the price to both buy and sell, break and form these different bonds. And so this energy is transferred when this happens. So let's take a look at this reaction. This happens in a hydrogen fuel cell. So the chemical reaction is H2 plus O2 gives H2O. So we're just making some water here. Okay? When a chemical reaction occurs, the enthalpy or total heat energy of a system can change. All right? I'm going to show you here. So if we imagine our two H2 molecules and our one O2 molecule, and we're going to break these bonds. All right? So we're going to put in the energy to break those bonds. All right? We spent that energy, we paid that price, that energy price to break those bonds. Now, when these atoms rearrange, new bonds can form that were different from the ones we had before. Right? When these bonds form, that energy is released. Right? Now, here's the strange thing. When we try to calculate this change in enthalpy, which is represented as delta H, change in, can be found with the following equation. We take the energy of the bonds we broke and we subtract the energy of the bonds we formed to find delta H, the change in enthalpy, the change in heat energy. Okay? So if we take a look at these hydrogen molecules, we had two of them, two of these bonds that we broke that were 432 kilojoules per mole, right? Plus this 1 mole's worth of oxygen double bonds, which are 494 kilojoules per mole. When these atoms rearranged and these bonds formed, we got 1, 2, 3, 4 OH bonds at 464 kilojoules per mole. So when we simplify, right, The energy we put into this chemical reaction is 1,358 kilojoules, and the energy we got out of this reaction is 1,856 kilojoules. The difference, or the change in heat energy, is negative 498 kilojoules. So our change in enthalpy is negative. That means heat energy overall exited the system. It left the system. That's why it's negative. Exit, negative. And so this process is called exothermic. Right? Now you'll notice we had to put some heat energy in to get this started, and we got some heat energy out. In this case, the heat energy we got out is bigger than the heat energy we put in, which is why it's overall exothermic. If we wanted to go through another example, here is the structure of C4. Right? It's a common explosive used in movies and TV shows for huge special effects, and it is extremely exothermic when it reacts. So we take this molecule, and we imagine it breaking down. All right, so something happens that breaks it apart, some energy is put in. These molecules reform and energy is released. And that heat energy is what causes this massive explosion that you see. So if you want to see this again, molecule breaks apart, the atoms of the molecule rearrange to form new bonds, and the energy released from those bonds is what you see as this massive explosion, this huge fire. So now we're going to look at a different example. In this one, we're looking at the chemical reaction that produces ammonia, which is used to make most of the world's fertilizers to grow most of the world's food. If we take a look at this one, we're starting out with a triple bonded nitrogen, and we have 3 hydrogen single bonds. We're going to pay the price, spend the energy to break these bonds, put energy in to break those bonds. It costs energy to break those bonds. And then, when those atoms have been broken apart, they can rearrange, and after they rearrange, we can form some new bonds. When that bond is formed, energy is released. Okay? So now we're going to use our equation as before to find the change in enthalpy, the change in heat energy from this process. So we'll take the energy of the bonds we broke and subtract the energy of the bonds we formed to find that change in heat energy. In this case, we broke a nitrogen triple bond. Whew, that one's expensive, 941 kilojoules per mole. We also broke 3 hydrogen single bonds, 432 kilojoules per mole, and we formed 6 NH bonds at 386 kilojoules per mole. When we put these together, we found that we spent 2,327 kilojoules to break bonds, and we got back 2,316 kilojoules when those bonds formed on the other side. Now in this case, our enthalpy change is positive. The heat energy overall entered the system in this process called endothermic, for enter. The heat energy has been stored in these bonds. Fascinating. Okay, so to summarize what we talked about, we can use the change in enthalpy using the following equation to tell us some things about a chemical reaction. So we used bond enthalpies from the table here to determine whether a reaction will be exothermic, releasing heat energy, or endothermic, absorbing heat energy. Reactions that release heat energy could be used as a potential fuel, or maybe an explosive, or maybe a hand warmer. And reactions that absorb heat energy are typically not as useful, but if the chemical we need to make with that is really useful, it might be worth our time to spend energy to make those chemicals. So ammonia, the one I talked about in the previous slide, is a chemical fertilizer. So even though it's endothermic and we have to spend energy to make that molecule, it is made all around the world all the time. All right, that's it. All done. Take the checkpoint quiz when you're ready.